Yeah, hello everyone. So my name is Piyush Behre. I work as an applied scientist in Microsoft, and we work in the speech recognition group here. I am presenting the work which my team worked on, and Sharman, Padma, and Chang, who are not here today, but they also contributed to this work. And so let me get started with what this problem is. What is this all about? Punctuation in long form dictation. So to start, let me just show here a hybrid ASR system, how it typically looks. So for a hybrid ASR system, there are two components typically. There's the audio coming in. So for the automatic speech recognition system, the audio could be a short form audio or it could be a long form audio. And in this case, we are looking at long form audio, which means it could really go on for a long time. It could be a 10-minute audio, 30-minute audio. So it's a continuous record that is happening. Then that audio goes into this first component, which is the first pass, or we call the decoder stage. And there are many subcomponents of this, which is acoustic model, language model, pronunciation model, or segmentation model. So all these sort of come together to figure out how to decode this audio and convert it into text. Now, the way the decoder works is that at various intervals, because it's a long form audio, so at various intervals, it's going to segment the audio in a certain way and try to emit that, because we don't want the users of this system to wait for a long time. We want them to see the output as soon as it's ready. So that's why for this system, it does have this segmentation model and tries to emit these segments, which are in the lexical form. So lexical form is basically spoken form. Audio, it doesn't have punctuation. It has some minor capitalization. It doesn't have number formatting. So if somebody says 8 p.m., it's going to be spelled out EIGHT 8 p.m. It's not going to be formatted correctly. So that's the typical system. There has been research to sort of do directly in the written form too, but here I'm just describing the typical system that's still in production in many of our companies. And so here, the final lexical goes into the second pass stage, which has again a bunch of features or models that get applied. Typically, you would see NNLM rescoring, so a large language model which rescores or ranks the N best within the segments. So within each segment, there's a list of N best, and they can be re-ranked based on a larger language model. And that tends to benefit in the word error rate scores. And then there are a bunch of these features which improve the readability of the output. So there could be things like disfluency handling, which is removing ums and ers and repetitions or false starts. So those sort of things can be removed if needed, and that makes the transcription cleaner. There's also inverse text normalization. So formatting for numbers, time, money, currency, dates, all of those things can be handled by this module. Then we have punctuation, and then we have capitalization. And after that, what comes out is formatted segments. So corresponding to each segment input that we have here, segment one, we have a formatted segment one, and so on. And then the user can be just displaying the output directly to some UX, or there could be another API consuming it. For example, there could be a downstream task of machine translation, which takes this as an input and then translates it into the target language. So something like that could be another use case for this output. Now, just the two things I've highlighted here is segmentation model and punctuation model. So these two are critical in making sure that the output is punctuated well, because if the input to the second pass is badly segmented, it's going to end up badly punctuating that, and then eventual result is going to be not good. So this work is going to focus on this aspect of it, that how can we improve the punctuation aspects. And we are keeping the segmentation model constant for this study. We have another research paper which also talks about the exploration we did for improving the segmentation model, but that is not in the scope for today's talk. So moving on to this. So next I'll describe the punctuation model itself. And typically it is designed as a tagging problem. And so the input, for example, here you look on the right, I am good. John, how are you doing? So this is the entire input in lexical form. So you'll see that this doesn't have proper capitalization. John is capitalized. It might be coming from an entity model, which is capitalized even in the first pass decoding. So that can still happen, but most of the things are going to be not formatted. It's all spoken form. Then we have a tokenizer stage, which generates tokens, and it goes through transformer encoder. And then we have a punctuation token classification head, which classifies the input tokens into these 4 categories, which is comma, period, question, or none. So that those tags can then be applied to the original text, input text, and then it generates this I am good, comma, John, period, how are you doing, question mark. So this model is supposed to learn how to put punctuation like this. And of course, for this task, in the past, there was a lot of, once LSTM was prevalent in use, then LSTM-based model was being used typically for this, and they tend to also run fast and they can be operated sequentially. So there are some benefits of that model. And then as when transformers came along, then the transformers started beating LSTM performance as expected for this task. So so today we do consider both of these in our approach of streaming punctuation to show that the system is indeed robust for both the models, and some of these models could still be in production for certain locales. So next, let me go and describe this part, which is one challenge that this model has, or one important aspect that we should appreciate, is that left context is not enough. So here I just show an example where all of these A1, A2, A3, A4 examples are in fact valid segments and valid sentences. So if the input to the punctuation model was it can happen, it puts a period after that, which is correct because it can happen as a full sentence by itself. Same could be true for it can happen in New York City, and it can happen in New York City, right? So all of these are valid sentences. So this is just to highlight that if the input to the punctuation model is segmented in a particular way, then it's going to also try to do its best with that limited input and just looking at that left context. So by left context, what I mean is there could be an example where somebody says, it can happen in New York City, and then there's this long pause, which the first block, the first pass decoder is going to segment after that long pause, thinking that, hey, it's over, this segment is done. But then that comes as an input to the second pass, and it ends up putting a period after New York and also after city. And that's a big problem. That's an over-segmentation. And that's a real issue that we face, especially in the dictation systems where users tend to look at their screens and wait for the output to come in, even in the middle of their sentences. And we see that happen quite often. And then there is complaints about, hey, your system is over-segmenting. And this is the core of the issue, that if we just look at the left context, it's not enough to really do the best possible punctuation for this input. So here is another example of just highlighting the same issue with a longer sequence of segments. So here there are 4 segments. And again, the user is pausing at the wrong places. And so it's producing non-ideal inputs and non-ideal outputs eventually from this punctuation model. So you have, how are you doing? How is your family doing? COVID restrictions can make it tough for artist families. I wish you could travel and visit more often. And like based on that input, you can see that there is over punctuation, questions put at the wrong places. How is question mark? And then the model is not able to do as well for this. Even no matter how powerful punctuation model you deploy, it's always going to suffer from this problem if the input is bad by itself. So how do we tackle this? So here are the key contributions for this paper. So what we are introducing here is a novel streaming punctuation approach to punctuate and re-punctuate ASR outputs, and taking into consideration the things across segment boundaries. And we demonstrate that the streaming punctuation system is robust to model architectures. So we apply this to LSTM models and we apply this to transformer models and show that it's beneficial to both the models. And then third, we demonstrate that it not only improves the punctuation quality itself, but also has a significant impact on the downstream tasks like machine translation, as demonstrated by the BLEU-score gains. So how exactly does this system work? So in the streaming punctuation system, what happens is that when you have an input, you break the correspondence of the input segment to the output segment. You basically look at the input segment and say that, okay, I see that there is one full sentence here and there's a potential partial sentence. And I'm not going to finalize this partial sentence until I see more input, which is going to be more right context. So here we only finalize how are you doing, put a question mark rightly there, and then we put the how is portion of this into the buffer. And we call this the dynamic decoding window, because next time we get more input from the new segment, we include this buffer, and this window expands and it figures out that how is your family doing is now a full sentence, and we are able to emit that as a full sentence. And we again keep going with COVID has been in the new buffer and so on. So if you see on the right, it is able to produce much cleaner output. Full sentences are coming out of this system, and that sort of addresses the over-segmentation issue that that I highlighted earlier. And of course, like one concern here could be that, hey, but is excuse me. So if the system is going to wait for such a long time, it's going to wait for more right context to come in. Wouldn't it be wouldn't have a lot of latency for the users? And in fact, yes, that could be the case, but it also depends on how you implement this. So in this case, we are not really going to wait for this whole right context to come in before we even display anything. Here, the display is still going to have how are you doing, which is a finalized portion of it. And then we also have how is, which is the buffer portion, is also going to be displayed to the users. And it's just that the buffer portion is the one which can later be updated. So that is the only difference here. But the latency at which users are seeing the output, the words from the output, that is going to be exactly the same. That is not changing. So it is, in fact, the user perceived latency is not going to be worse than the original system in this case. Next, let me just describe the data and the models a little bit for the experiment, and then we can go over the results. So the data that we use for the training, the punctuation models, both the LSTM and the transformer models, they use the same training data here. And so we leverage a bunch of these sources, open web text being the biggest one. So this is the data set that consists of web content from URLs shared on Reddit with at least 3 upvotes. So there's some sort of filtering criteria to make sure that good content from the web is covered. And this has roughly 40 million paragraphs that we generate. So the definition of paragraph for us is we basically use BP units. So we have 32,000 BP units, and we chunk the inputs into 250 token paragraphs. So anything, all full paragraphs that can fit within 250 words is going to be the input. So we have roughly 40 million of those from the open web text, which is roughly half of the corpus here. Then we also have Stack Exchange, which is really good at some of these more technical terms and equations, math equations, and questions, a lot of different ways that people ask questions at Stack Exchange. So that's really a good data source for the punctuation task. We have Open Subtitles set, which is a good source for conversational style data. So it could contain a lot of these different pauses, and the model can learn a lot from the conversational style element, which is not as easy to get from the web. Then we have the earnings call corpus. So these are transcribed earnings calls based on the S&P 1500 companies. So we have a lot of that data. And then we have the NPR podcast data. This is, it's less of that because the availability of fully written form of the podcast data is quite low, even though the podcast data itself has been growing in the recent years. The availability of good display form podcast is not so much. But anyway, so we use all of this to generate those paragraphs and train the punctuation model. And then for the testing, we have 4 sets, which is trying to cover all the different flavors. So we tried to basically cover three different flavors with punctuation. One is the human-to-human case, which can also be called conversational. So if there's a one-on-one conversation or a small meeting conversation, those would count as human-to-human. We have human-to-machine, which is dictation use case. The users are interacting with machine to dictate a document. So we have the dictation set, a dictation 100, which consists of 100 sessions of these dictation sets. And on average, these are 3-minute long. But it still has a lot of, still has a chance to sort of experience that over-segmentation issue. It is a good set for just to highlight that part of the problem. Then for earnings call, we take 10 hours of the earnings data. And this is more of a human to human, or we can call it human to group, which is a broadcast use case. So for the first part of the earnings call, typically you have the CEO or the CFO of the company speaking, and then that's more like human to group. But then in the later part, it becomes more conversational, where the analysts are asking and the company management is replying to those questions. Then European Parliament is also a human to broadcast use case, where one person speaking at the Parliament sessions, and then we have 100 of those. So for this set, we also got those to be translated into seven different languages for our downstream task experiment, and also in the written form. And then we have the podcast use case, which is typically just conversational between 2 or 3 people. So with that, the models that we train, we have 2 models. One is the LSTM tagging model. It's a 1-layer LSTM with a 512 dimension word embeddings and 1024 hidden units. For this model, we do use a 4-word look ahead. So our decisions are delayed by 4 words, so that it at least captures some of the right context. But the right context is still limited to within the segment in the baseline model, and then in the streaming model it can go beyond the segment boundary. So that's the main distinction. And then the transformer model has a 12-layer transformer with a 16 attention heads and 1024 dimension word embeddings, and we have 4096 fully connected layer. And we do have an 8-dimension output here, which is more than the 4 tags that we are trying to output, and that's okay. It just outputs null for the other ones. And then for both of them, we use a 32K BP units. And like I said, it's trained on 250 BP unit BP token paragraph sequences. So let me pause here in case there are any questions, and then I can keep going over the results. So firstly, we look at punctuation results. We generate precision recall F1 scores for period, question mark, and comma. These 3 are the main categories that we cover. And we look at F1 gain. So the main thing to look at here is that for both the systems, we are not comparing LSTMs with transformers here, because of course transformers are going to come out ahead compared to LSTM. We are trying to compare streaming LSTM, that's denoted as ST LSTM, comparing that with BL, which is baseline LSTM. Same for transformer, we are just comparing it with the baseline transformer system. And indeed, for F1 scores in the punctuation metrics, we do see some improvement, but it's sort of not, it's not looking as high as indeed the experience is. And because one thing to note here is that if we just look at the period use case, and we look at the precision recall, the main benefit is the tilt that we obtain. So in the baseline system, we see a lower precision number and a higher recall, which is an indication of an over-segmentation problem. The system is trying too hard to get that high recall and trades off the precision. So the new system is able to get higher precision, lower recall, which is in fact what the users really prefer as well. That, hey, only give me punctuation when you're really confident of it, and otherwise don't bother, because if you're too aggressive, then I need to go and edit things. So that's basically the feedback that we receive from users, and this nicely addresses that feedback. So like when we originally were going after this work, we had the dictation use case in mind, But we do see similar benefits for some of these other use cases where the speech is still continuous, but maybe the breaks are still happening at the unusual places. So if you look at the earnings corpus, again we see the switch, and then the EP, the European Parliament corpus, again we see the precision recall switch that happens with a streaming transformer. In this case, it's more paired, but still compared to the baseline, it's looking much better. Same for NPR. And in fact, for segmentation, we also look at segmentation F.5 as a measure, which gives a higher importance to precision, lower importance to recall. And that is based on the user feedback as well, that, hey, if you have a higher precision system, I prefer that. And for that, of course, the numbers would look higher because we are giving more weights to precision. So this just again highlights that same property here, that okay, it is indeed improving on segmentation score, segmentation F1 and segmentation F.5. Both are improving. Then finally, we look at the benefits of this system to the downstream task of machine translation. And here, these are the locales, which are the target locales for the system. And so we still apply the streaming setup to English, and then the output gets translated into these languages. And then we have reference translation also in those languages available. And then we compute the target BLEU scores for these. And like, as you can see, for most of these cases, we have a BLEU score gains. In fact, for the transformer model, we always have a BLEU score gain, even up to 1.4 BLEU score points, which is considerable, which is considered quite high for any translation research purposes. And even for LSTMs, there's a win for 5 out of 7 categories. There is some regression that we see for French, and then for, I think there's one other locale that with this, yeah, there's for Portuguese also, we see some regression for LSTM model. But for transformer, it wins 7 out of 7. And it is worth noting that for some of them, the gain is quite high at 1.0, 1.1, 1.4, which is sort of indicative that for certain locales, the punctuation is quite useful as an important feature for doing translation better. And for certain locales, it does seem like that the translation is more robust to punctuation errors. And that's what we see with some smaller gains for some locales. So that's our observation. But I think overall, it supports our hypothesis that it still helps the downstream tasks by doing the streaming punctuation setup. So with that, let me conclude by just recapping the results. So we do see streaming punctuation to be effective across model types. We saw the improvements for streaming transformer over baseline transformer system, with a segmentation gain of 13.9% and punctuation F1 gain of 4.3%. Similarly, for the streaming LSTM, we saw a 12.2% average gain in segmentation F.5. And then we have an F1 gain of 2.1% over the baseline LSTM. It is also found to be robust across scenarios. So we saw the performance for long-form dictation, human-to-machine, and then also beneficial for conversational human-to-human or broadcast, which is human-to-group scenarios. And so it establishes that this technique is quite robust for all these use cases. We do see a higher quality, that the higher quality punctuation leads to higher quality downstream tasks. For instance, the BLEU score gains that we see for the MP task here. This is the average gain that we see for the LSTM technique and the transformer. And so in the future, what are we going to explore? So currently we are exploring more prosody-aware punctuation models to recapture any decoder segmentation signals lost. Because what we have done now is we sort of discard the decoder segments completely, but there is some good value in decoder segments because decoder is acting on audio input and there are audio cues that it captures, but our text-only model discards that. And so there is possibility to improve this further by having a model that incorporates those audio signals or prosody signals. And that's something that we are looking at. The other thing we are looking at now is with more E2E models, replacing hybrid models, we are also exploring how this technique is still beneficial. And indeed, like early results do show that this technique does apply to E2E equally well. And so we'll be publishing those results as well in the future. But yeah, anyway, that is my presentation. Please go ahead and ask any questions that you may have. Thank you.